before the pandemic, and then it took a little break, and then started back up in 2023. I think this is maybe our fourth Climate on Tap since the pandemic. And so today we're going to be hearing from Bob with STARS Technology, and he's going to be telling us about bending the emissions curve. So let's give Bob a welcome.
Thanks very much. I commented earlier that I need to tell who I am now, so you'll know why I'm qualified to talk to you, so no one will ask the question at the end, why did you think you were qualified to come and talk? That would be embarrassing. But I'm saying that to say I want to have some fun with this talk. This is the third time I've talked to this group before. The first two times were before the pandemic. Once it was at the Emerald of Siam. Some of you were here for that. The next time was at that, was it called Paper Street or something like that?
The Paper Street Brewery.
The pub that was there.
Yeah.
So I gave another talk there too. This talk is a little different than those first two talks. At that time I was talking about clean energy from a conservative's perspective. Some of you know that I was a precinct committee officer in the Benton County Republican Party, and I may be one again next year, and then again it may not be. It may depend upon how some things go. But I want to also mention that I usually put stuff in the slides to remind me to say something that otherwise you might not have known about. So by the way, the subtitle, If I Had a Hammer, that's sung by Peter, Paul, and Mary, it's really meant to remind me that I wanted to say to this group that I really appreciate this local CCL group. You guys are working hard to get information out there, to help the public understand what's going on, to get legislators to do things, etc. That's part of why it is really fun for me to come and talk to you guys. We don't always agree on some points, but we're all in this together. We're all trying to work hard to solve the climate problem. STARS Technology is part of that. Dennis Walters is here too. He's part of STARS. My wife, Dorothy, is over here. Wanda Walters is there too. She's just as much part of STARS as Dennis is, I'm sure. Maybe sometimes you feel like you give up even more to it than Dennis does.
Can you explain
But I wanted to
STARS?
comment.
Can
Oh, what's that?
Explain what STARS is?
I will.
Okay.
I will, but I'm not going to do that yet. That's on the next slide. Or maybe it's a couple of slides further on. We'll all find out in a minute. We'll all find out in a minute. But I do want to say, I want to provide a warning. This is for mature audiences. This is not for people that are skittish or things like that. We may break some things during this presentation. We will definitely be talking about paradigms. We may break some paradigms. We may be dancing on top of the shards of some paradigms by the time we're done. Paradigms that are false need to be exposed so that we can make better decisions about how to do things. And developing paradigms that work so we can teach them this also matters a lot too. So to a large extent, this talk has to do with paradigms that relate to the next three things. One has to do with the title of this. When I was asked about a title, I said, how about bending the emissions curve? Because I kind of knew that I would want to talk about that. I also knew, because I'm with STARS, that I would want to talk about things STARS is doing on establishing carbon-negative renewable hydrogen as a clean fuel. That's related to paradigms too. And then the third thing I'm going to talk about is something that Steve and I have spent some time on the continued efficacy of the natural carbon sinks. So I'm going to talk about all three of those things. And again, I hope to have a lot of fun. Hopefully, I will continue to occasionally make you laugh. Sometimes it'll be at me. Sometimes it'll be at things I say. Sometimes there might be stuff on this. But there will be an occasional item simply to remind me, oh, at this point, make sure you say this or make sure you say that. It may not be obvious to you that that's what it was for. I was asked earlier, if I had a hammer, did that mean that we were going to sing or that I was going to have music playing with this? And the answer is no. That was to remind me that I think of this group as an advocacy group. I was born in the 1950s. I know who Peter, Paul, and Mary was. I think a few of you do too. You knew who they were. So let's go on to the next slide. And I said I will talk for a moment about who is STARS Technology Corporation and what we're about. So by the way, Simon Sinek wrote a book that says start with why. This is about corporations. Don't start with what, but start with why you're there. And I thought that was great advice. So I'm going to talk about three things on STARS. The first one is STARS' just cause, why we're out there. What is the reason for doing things that really will matter in the world? And our just cause is to deliver to the world an affordable, sustainable energy future. I'm a technologist, I'm a thermodynamicist, mechanical engineer, and a few other things. STARS is a company developing technology that we have licensed from P&L. I was part of the development of that technology while I was at P&L. You'll see more about that in a minute. And I want to cover the second part of the Start With Why, our objective, and that's to provide new, modular, low-carbon, and renewable energy and fuels technologies that are economically preferable, economically better than the fossil fuel technologies that are out there today. In the 20th century, engineers became very good using technologies to do certain kinds of things, including energy production and chemical production, etc. We developed paradigms about how to design them and where to site them and how to do this stuff. But it's the 21st century. There are new advanced technologies that break some of those paradigms. And we need to learn to think in different ways than we did in the 20th century. The 21st century is a lot about replacing the 20th century, but with things that are economically better than what we did in the 20th century. And the third one is our first commercial product, a mass-produced compact hydrogen generator that uses breakthrough microchannel reactors and heat exchangers. I'll tell what those are a little bit in the presentation, to efficiently produce affordable clean hydrogen where needed. And then I'm going to bring this up again. By the way, there may be a quiz at the end of this. I have one question in mind. I'm not going to tell you the question, but I will tell you the answer. The answer is economies of hardware mass production can compete with economies of scale. That has to do with these paradigms for the 20th century compared to the 21st century. So when I ask the question later about that, about what's the answer to the final question, you don't need to know the question. You just need to remember the answer to the question. Maybe I'll come up with a question for which that is the answer. So I now want to do a little preamble. Something about goals and objectives. I was an engineer for a long time, and projects for a long time, and organizations for a long time. I kind of like when somebody came up and said, you should have high-level goals and a series of objectives under them that you can measure so that you know when you attain the goal. The objectives should sum up to say, now I met that goal. I like that approach. I view the temperature-related things in the Paris Agreement as being the high-level goals. And you guys probably know also a few pages in, my PDF copy of the Paris Agreement is 25 pages long. There are lots of words in it, but we only hear a little bit about some of them. So anyway, from about 2 or 3 pages in, there are 2 goals that we hear about often. I refer to these as overarching and possibly over-reported goals. The first one is to hold the increase in global carbon temperature to well below 2 degrees C above pre-industrial levels. I would be amazed if people in this room didn't know about that goal. I would be even more amazed if they didn't know about the second one, which is to pursue efforts to limit the temperature increase to just 1.5 degrees C above the pre-industrial levels. And again, I think this is over-reported to a certain extent. We see this practically every day. There's always going to be an article in the news or in the trade journal or something where they talk about our problems with accomplishing, particularly the 1.5 degree C goal. And they often report that scientists have told us that at 1.5 degrees C, the Earth will start to experience irreversible climactic type events, which of course isn't really what climate scientists have told us. But it is the popular thing to talk about on the news, and it helps people continue to stay on the news stories so that they get to see the commercials that people paid to have put on the show. We hear about those a lot. But now I want to go to the objectives part, and this is where I think there's stuff that's really valuable, but possibly underreported. Technical objectives to achieve the long-term temperature goal. That's in the item. A couple of pages past those first. So 2 objectives. One is to reach global peaking of greenhouse gas emissions as soon as possible. I'll come back to that in a second. I want to bring up the second one. To achieve a balance between emissions by sources and removals by sinks in the second half of the century. Now I said I'd like to see objectives that are measurable. It would be a little better if the first objective didn't simply say as soon as possible, but gave something more concrete so we could see how we're doing. And the second one, at least they gave a little bit more. They say in the second half of the century. I wonder if the authors thought, will that be like in the last quarter of the century, after 2075? Will it be between 2050 and 2075? But they surely didn't think our goal is 2030, or our goal is 2040, when they wrote in the second half of the century. Roger, you asked me before, is there going to be good news? Maybe, on these points, maybe. Now, I want to mention, I'm kind of jumping to the first item. this is like getting to the end of the story first. The International Energy Agency projects that the world will hit peak anthropogenic CO2 emissions during this decade, perhaps as soon as next year. Almost 3 years ago, they made that announcement. They said that the war in Europe put great pressure on energy replacements, and that has made a big difference in the production of renewable energy and other things too, so that they were now projecting, again almost 3 years ago, that wow, we could hit this peak emissions, that's the first of those two underreported goals, perhaps this decade. They announced that. I got to watch on TV on YouTube, I got to see their announcement of it, but it's hardly ever reported that they had said that. It's also hardly ever reported that last year they came back with more information. That's when they said it could be in 2025. A few other groups have said, yes, we see it that way too, and a couple have said maybe this year we hit peak worldwide CO2 emissions. Oh, I forgot something. Sorry, I forgot to make an important comment at the beginning. When I say CO2, I mean carbon dioxide. I don't mean methane, I don't mean N2O, I don't mean refrigerants, I don't mean ozone. I'm not talking about positrons and whether they go backwards in time like Richard Feynman suggested. I'm definitely not covering the many worlds view of quantum mechanics. And I'm not talking about who should be the next president. In fact, I've learned that I shouldn't be the one telling people who the next president should be. Important things like that should be communicated by my wife. But anyway, the IEA says that. So I want to talk about this for a couple of slides. Again, this is that first item about reaching peak CO2 emissions. Again, the good news from the IEA was that. I'll talk more about it in a moment. But first I want to say, what's the progress in the USA? Well, again, an underreported item is the USA hit peak CO2 emissions in 2005, maybe 2006, but the USA did it years ago. We've since shut down over 300 coal-fired power plants, over 300 coal mines. We've done it through a combination of things that include shifting some power from coal to natural gas, that include solar and wind generators as well, that include some batteries in places too. But we have substantially reduced our CO2 emissions. We'll show that now. So this is what the Energy Information Agency from the US put in a chart about a year ago. This is from their Annual Energy Outlook 2023. I don't think they came out with one for 2024. When I looked for it today, I found a website that said, stay tuned next year. So they were saying, we'll have a 2025. I think maybe they didn't do it 2024. But this is the chart they produced. And it has what I was talking about. In about 2005, we had peak CO2 emissions. And again, this is CO2, not CO2e, but CO2. And since then, it's been declining. Now, their projections a year ago in 2023 did not include things people talk about, which is, can we get to zero in 2050? They say they were confused about the Inflation Reduction Act and its provisions. So they have one scenario without it, they have a couple others, but they basically said stay tuned for the next time around for what we think that will do. So, but I will certainly say, my comments on this is that their report certainly were disappointing. If we really want to get much greater emission reduction, they showed emission reduction slowing down. And we all know we can do better than that, and we know we need to do better than that.
Price on carbon.
That's one approach, but I would say there are other things too, and I'll talk about some of the others as well.
Okay.
Yeah, don't be a heckler. Now, worldwide, I said before that the IEA has said we think we can hit peak emissions during this decade. So now I put up a chart. By the way, Mickey had said don't be too technical. So if this is too much, then please avert your eyes. Again, this is mature audiences only. But I produced this chart. There are only a couple of charts in this that I didn't produce. I'll just let you know. So that means it's not too technical. If it's not too technical for me, then you guys can handle it too. But what this shows is emissions. It says emissions and sink removals, but I took out the sink. I just didn't correct that part. So this is just annual emissions from the world, anthropogenic emissions over time. And this is what they were. And the interesting thing about it, and again, I chose the color coding, that in about the year 2012, we went from exponential increase in emissions to something that's flattening. That's very consistent with what the IEA said. I produced this because I wanted to see, are their words tracking the history? And it looks like over the last 10, 12 years or so, We've gone at a different angle. And that's good. In fact, again, it means we're no longer on an exponential growth rate.
I thought it peaked in 2005, according to the earlier data.
What's
I
that?
thought the peak was in 2005.
The USA peaked in
USA.
2000. USA peaked. The rest of the world, not so much. And I think we all know that China and India have produced a lot more coal-fired power plants in the meantime, though they are trying to push it a different direction too. Now this one I did not produce. This is coming directly out of this report from the International Energy Agency. This is the one that I would recommend most strongly if you want to read what they say about why we are bending the emissions curve. And that's their term, by the way, bending the emissions curve. I just like it a lot, so I stole it. But they talk about solar photovoltaics, production of them going up, and deployment. Likewise, I can't quite read these. That's electric cars. This is residential heat pumps. This is battery storage. What they're basically saying is that modular systems mass-produced, as they achieve greater and greater of mass production rates to build these systems, they get cheaper and cheaper. We knew that to be true already in the USA, but they're saying it's happening. It's happening so that now we are getting modular low carbon technologies out there that are economically competitive with fossil energy technologies. Now, I think we all know that as they become cheaper than fossil energy technologies, then people will tend to prefer the clean energy technologies instead. So that is a paradigm notion then from the IEA about how to reduce carbon emissions. We have to deliver technologies that are economically preferable and they cause emissions to fall. And I want to make this point too. This is about paradigms. The world is departing from the IPCC, the UN's International Panel on Climate Change, from their business as usual scenario. And the stuff I've seen coming out of them as they prepare for their next round is a recognition that they need some other kind of standard, because we're not on a path now where we keep doing the exponential growth up. Hopefully we don't take it again. But if we're not on that path, then we don't need to be comparing ourselves to scenarios where we're at 1,000 parts per million in the atmosphere or 1,200 parts per million in the atmosphere. Instead, we're on a path where we could definitely go less. And by the way, it's up to us to make sure that happens. So while Roger, there's good news in this talk, the bad news is it's still up to us. We still have to work. Now, I wanted to say something about mass production. You guys remember there's a question at the end. I'm not going to tell you the answer anymore. It might have to do with this. So I'm going to show first Henry Ford's mass production. As a mechanical engineer, I studied that. And it fascinated me that over actually about 2 decades, Henry Ford transforms transportation in the USA immensely. Well, anyway, so the IEA pointed out that Ford achieved 70% cost reduction over 10 years through assembly line mass production. But Ford started off, as the subtitle says, he started off saying, I want to do a mass-produced automobile. When Ford began, everyone knew that only a rich man could afford a car. They were thousands of dollars each, and that's the start of the 20th century when $1,000 was a whole lot of money. Ford said, if I can design a car for mass production and get the much better efficiency of labor through things like assembly lines, then the average family will be able to afford a car. This is part of why, and I showed these pictures, like a comedian, I don't want to tell the same jokes all over again. I showed these pictures a couple of talks ago. New York City in 1903, it was Easter Sunday, black and white photos. It's hard to find the car in the photo. It's loaded with horses and buggies. 10 years later, same place. It's loaded with cars. It's hard to find the horse. That only occurred because in that 10-year period, it went from a circumstance where if you owned a horse, but it was time to replace your horse, you were economically better to get a car. We want to think that way, by having clean energy technologies that are better solutions than the fossil energy technologies. We change the planet whether the planet wants to change or not.
Workers were able to buy the cars they were making.
Yeah.
So now, this one, I like this one a lot. This is from World War II. World War II, and then World War II, the USA mass-produced Jeeps at the rate of 1 every 2 minutes. They came out of the factories in the crates, ready to be put on ships and taken to Europe. There's a really great YouTube video. I put it here at the bottom. It's a great YouTube video. It's part of a series on how America won World War II, on how America's manufacturing might won World War II. And it talks about how we changed out things in Detroit and elsewhere. How they changed out assembly lines for mass production, and how they changed the design of things like machine guns and jeeps and, well, not so much jeeps, I think jeeps were new then, tanks and that sort of thing. So they could mass produce them and get them into Europe and train mechanics so that we could be servicing them in Europe as well. It was a major part, and it's a really great set of YouTube videos, but the one on General Motors is the one which will show you the Jeeps. I really like the bit about the Jeeps. So now I want to segue. I said I'm going to talk about three things. That first part was about bending the emissions curve and what the IEA had to say about that. Now I'm going to talk a little bit about STARS. How long have I been talking?
25 minutes.
What?
25 minutes.
25 minutes? Oh, okay, so I'll be done in about 3, right? The next 15 slides are really fast. Okay, so now this is kind of like the talk within the talk. And I've got the disclaimer here. This is whenever I give a talk for STARS, in case somebody in the audience thinks they want to get so enthralled they want to make an investment, I have to put something in here that says, you do these things at your own risk, you listen to me at your own risk. But I'm going to be talking about what STARS is doing to produce carbon negative hydrogen from biogas, renewable natural gas, water, and electricity at a low cost. And we are using, as I mentioned before, technology that I and others were developing at P&L going back 30 years now. It's hard to imagine that we've been working on that long. Microchannel reactors and heat exchangers and separators are extremely process intensive. It allows us to increase the heat transfer rates per unit volume by a factor of 100 compared to conventional technologies. Chemical process units that are heat or mass transfer limited, therefore can be shrunk in size by a factor of 100 with the same production rates. So for example, Dennis, didn't you bring, yeah, this is a plastic model of one of the reactors that we're doing. I'll show you the reactors in a minute. But this is actual size. It's a little less than an inch thick and about 11 inches in diameter. For the hydrogen production productivity we get from this, to do the same thing with conventional technologies, it would have to be 8 feet tall. That's light. I had to bring this because it's light. The metal reactors are actually kind of heavy also, and my back doesn't like that for me to do these steps with that. But there's no way we could carry that in. We would need more than a forklift to bring something that large in. Being able to mass produce these things makes a big difference. So we get 100-fold process intensity within these size devices. We refer to them as chemical process chips. They're analogous to computer chips. Again, you make this system, the components inside smaller, and you get much higher productivity out of it, including sometimes substantially better efficiency as well. This is the SolidWorks model of what we built and have operating. I'll show pictures of it in a moment. But this is one of the actual reactors, about 10 inches in diameter in this case. We're inductively heating them. If you think about the new induction cooktop stoves, so you can put a metal pot on and heat from under a ceramic, we put copper coils on each side in order to provide the heat for the endothermic steam reforming reaction. Normally, industry would have to burn a fuel to do that, and there's CO2 from that. We don't have to burn a fuel to do that. In fact, we're considerably more efficient at providing the heat for the reaction because of this nature. And this also shows a microchannel heat exchanger. Dennis, you got one of those too. Why don't you just hold it up? That's the same size as the unit there. So think of that entire system as being about this tall. And you can put a lot of them together. So if I said I'm going to take the table over here, setting them side by side, obviously I could get 8 or 10 of them on that table, and therefore be ganging up to do high volumes of mass production of hydrogen near where I need the hydrogen. I'm not going to talk through these details because I'm just going to go right onto the picture. So the chemical process unit is a footprint of about 1 square meter. It's got 3 of those reactors side by side, other heat exchangers and other reactors in it too, a pump, valves, other instruments, etc. So this is a unit, in other words, a little bit bigger probably than the refrigerator in your house, which means we can mass produce them, put them on wheels, and we can move them through an assembly line and mass produce them. Normally, chemical engineers use economy of scale to get low cost. So they build something a lot bigger than this building in order to get to low cost. We get to low capital costs by mass producing the hardware, just like Henry Ford's automobiles, just like those Jeeps, just like flat panel displays, just like a lot of other things too. We get to low capital costs that way instead. So this is consistent with the IEA's observation that modular, mass-producible clean technologies will be able to beat out the older economy of scale-based fossil energy technologies. We've been working this for years. We were delighted that the IEA is a great front man for us, saying this is how you do it. And by the way, this was assembled. This picture was at Highline Engineering near the Richland Airport. So here as the system is down in Southern California in Palm Springs at Sunline Transit. Our partners on this include Sunline Transit, Highline obviously, also Southern California Gas Company. They're mentioned over here. They are the nation's largest natural gas distribution utility. They've got about 20 million customers. They paid a lot of the cost for this demonstration. We paid some of it too. Sunline Transit has about 30 buses now, Dennis? 26, I was close. 26 buses. Well, I got one of my props here. I can change it to 30. Yeah. But anyway, the real point is that's the unit there. There are other peripheral items too. At the unveiling ceremony a year and a half ago, the vice president from SoCal Gas made some comments, and some got turned into a press release. They talk about the potential to provide clean hydrogen at any location adjacent to a natural gas pipeline. We use renewable natural gas brought through the pipeline. So that means it comes from farms, from anaerobic digesters and elsewhere. It's stuff that would have gone up into the atmosphere. Methane, we know, is a super greenhouse gas. Converting it to hydrogen and CO2 reduces the greenhouse gas potential. When a GREET assessment, and if you know what that is, if you don't know what it is, I don't have quite the time to explain it, but a GREET assessment performed on this makes it carbon negative. California scores now all the compressed natural gas at the 300 plus filling stations they have for CNG. All of them, they score them as roughly minus 100 grams of CO2e per megajoule because they are using renewable natural gas, again, sourced from anaerobic digesters, landfills, manure pits and agricultural sites, etc. It's a wonderful thing that's happening. And by the way, I didn't look it up. I should have looked it up today. Last time I looked it up, the price of that renewable natural gas at those filling stations was something like $2.30 per gallon gasoline equivalent. California's about $500 a gallon for real gasoline. So you don't get that kind of price unless everybody in that value chain is making money. You don't get 300 stations all getting that unless people are running around saying, where is the next place I can go source renewable natural gas? It's a wonderful surprise that it's that way. But I want you to imagine these chemical plants, again, the size of a refrigerator, or twice a refrigerator, manufactured through assembly line mass production, again on wheels, shipping from the Tri-Cities. We can put them in crates just like those Jeeps, ship them all over the USA, all over North America, really all over the world. Basically, we can flood the world with affordable clean energy technologies from biogas for hydrogen. That's part of where we're going with all of this. And again, if you all want to throw in money into this, that's fine, but don't pay any attention to me. It's at your own risk. But I want to also say a little bit about the architecture. So where would we ship them? It's a question I'm supposed to ask that goes with this one. And again, if we're going to be the equivalent of about $5 per gallon of gasoline for the hydrogen initially, well, distributed hydrogen production is enabled by this approach. We can put them at the filling stations. Again, with the natural gas grid nearby, we can make hydrogen near to that. This is for both transportation and distributed electrical power generation. If you know about the regional hydrogen hubs, I'll show you something in a moment on that, but this can help fill out and connect the hubs around the country that are being set up. Again, delivering the renewable natural gas through the gas grid gets us to carbon negative hydrogen. And we believe we can have these units in mass production in about 18 months. And then this shows you where we're leading to. So by the way, you guys will recognize this is the Northwest. The darker counties are the ones that have the most biomass. The lighter ones have less biomass. We're showing with the red lines where the current natural gas transmission lines are, the high pressure transmission lines across the country. The little white dots are communities. They don't show up very well from my angle. Okay, the yellow lines are major highways. By coincidence, communities and natural gas lines tend to go near highways. They all seem to be on the highways. And in addition, I'll say that the blue circles are the places in the Pacific Northwest hydrogen proposal for where they said they would put some electrolyzers. The green hexagons are our notion of us deploying our systems in communities on the gas pipeline, at filling stations, etc. our individual units on it, and again, connecting. So there's a hydrogen hub way down here. There's one up here. We can connect these and open transportation routes throughout the entire country this way for hydrogen. Now, in the Northwest, we don't hear a lot about hydrogen in vehicles. There are currently about 70 hydrogen filling stations in Southern California. And as I recall, about 20 or 30,000 passenger hydrogen cars down there. At the moment, the hydrogen filling stations rarely have hydrogen. And when they have it, it's way too expensive. That does not encourage the production of hydrogen vehicles, et cetera. And the hydrogen right now down there is typically about $30 per gallon of gasoline equivalent. By being able to deliver it at basically the same price as gasoline, we change that. And by the way, a hydrogen fuel cell vehicle is about twice the efficient as an internal combustion engine. So in that case, it's like paying $2.50 a year. So we get to completely reverse that false paradigm that said it would make sense to be delivering hydrogen from far away to those filling stations. And we get to do this rapidly. So we're saying distributed production departs from classical paradigm of central chemical processing. It offers this new paradigm for distributed processing. And we believe the fastest approach to building a clean, affordable hydrogen grid.
So is it only focused at the transportation sector right now, or will we be focusing on industrial use of?
So that's a binary thing. I'm going to say we're not focused on just one, but what I will say is the problem right now in California of about 20,000 vehicles that can't get affordable hydrogen creates an opportunity. In the Northwest, we don't have those vehicles. If I start placing the ball over the Northwest next week, nobody's going to them because they don't have the vehicles. If I solve the problem in California first, then the company gets the cash to build out and do much more. But it's not just transportation, I mentioned, it's also electrical power generation. So if we think about the need for more power generation, for energy storage, to support the grid as we build up more solar and wind, that's intermittent. Placing these units, which use electricity, remember, I'm using electrical heat to help run these reactors. Placing these units that use electricity to make hydrogen at the communities where there is already a electrical distribution grid. It allows me to also produce power to back up the intermittent wind and solar, power at a low cost. So to me, it's really kind of starting with both of them as a focus, but later it will also be industry and some other things.
So how does the cost of your way of producing hydrogen compare with production by photolysis or by
The electrolysis.
electrolysis? Yeah.
I do have a chart like that, but I didn't put it in this slide set. So you're going to have to ask me back.
Okay.
No. But I'm going to preview the answer. We believe when our units are mass produced, it costs about $3 per kilogram. That's per gallon of gasoline equivalent because a kilogram of hydrogen has about the same energy content as a gallon of gas. We think it'll cost about $3 per kilogram, plus or minus 10%, to be making the hydrogen. If you do it with water electrolysis today without subsidies, you're in the neighborhood of $7 to $10 per kilogram for the production of that.
Well,
Dennis?
at Sunline, the director of Sunline told me they're paying $21 down there with the electrical costs in California per kilogram.
Oh, right. So I'm thinking Northwest is cheaper, but in California, they've got an electrolysis unit at Sunline. And they were quick to say, yes, bring this demo down there because they would really rather have much cheaper hydrogen.
But that cost includes when there's a surplus of energy, in other words, it would normally be exported.
I was going to say, because the energy is exported, are you talking about the cost in the Northwest?
Well, the electricity supply, yeah, in other words, it's being used, when you said you were using electricity. When the dams basically during spring have, I don't know how the price is.
In our case, we were simply using the average price of electricity over the year for a region. That's what we were doing for our month. And we do the same thing when we work electrolysis and others.
I just had another quick question, Brian. So can the scale, I mean, the real application, I think, for the hydrogen is on the long haul trucking, rigs and fuel cell there. So the alternative fuel corridors, are these at scale to be able to provide, support a fueling truck stop hydrogen fueling?
So I'm going to answer that in part by pointing out paradigms again. So right now there's a new paradigm that says everything will be electric. We'll all have electric cars in the future. So we won't want hydrogen for our cars.
Right.
Now the people that are saying that are noting though that if you put those batteries in a semi-truck, you give up about 20% of the payload of that long-haul trucker,
Right,
just to move the batteries. So the paradigm that's false, but that's emerging, is that, well, it's really for long-haul trucking that we'll do hydrogen. But the truth is, from an economic perspective, when hydrogen and fuel cells give you better, more affordable automobiles than battery electric vehicles, you'll like the hydrogen case. It'll just like when the automobile was better than the horse, and economically, people went to automobiles. So I don't believe that paradigm that says, well, this is really for long-haul trucking and transportation. I don't believe that's true, because we can get much cheaper than the electricity case.
And the trucking would probably be the first economic.
Yeah, see, that's- that's
Except
the
for
real-
in California, where right now there are 20 to 30,000 vehicles, passenger vehicles, that need hydrogen now.
Trucks and fleets.
And by the way, we also like buses, so fleets. We're not pushing away from those. I'm just saying I don't agree with the paradigm that says it's about long haul or long distance and only fleets.
But you could provide enough modular units at a truck stop basically for hydrogen.
Oh, definitely,
Yeah,
definitely.
that's all I wanted.
I'm sorry, you're right. That was part of your question, and I kind of flew past it.
Can I add one more thing here, Bob? I understand there's about a 3,000 acre photovoltaic farm going in somewhere out in Hanford. And when that happens, there's going to be a whole lot more power when we don't need it. And this is a great application coming back to transportation would be our focus normally, because that's where the demand is right now. But here in our community, using that surplus power to make hydrogen and then bring it back on the grid when the sun's going down.
Storage, yeah, storage,
later in the day.
energy
It's a battery source, yeah.
Yeah, it's a storage, yeah.
So now, just a few more slides. I want to now segue to that third item. I'm going to talk about the natural carbon sinks. And I'm talking about the biomass on land as one category of carbon sink. And I'm talking about the ocean, dissolution of CO2 in the ocean, and all the things that happen then as the other category of carbon sinks. And now I've got one of those little things there that you wouldn't have noticed otherwise, but I put it out. This is to remind me to mention Steve. So Steve has been working with me on this, providing advice and doing his own parts of it as well. I put this up because I just thought I'd be so embarrassed if I didn't mention it. So I want to talk about the continued efficacy of the natural carbon sinks. And I'm going to base a lot of this on the information from papers that about 110 authors do every year on the global carbon budget, really looking at CO2 and carbon throughout the entire planet, sources and sinks, etc. Friedlingstein is the lead author on that nowadays. But by the way, this first one is not from his. This is from the Mauna Loa data. And again, I produced this chart myself, proving that I can use Excel to make charts. So this is CO2 levels as they've increased from when they first started in Mauna Loa, taking the data, up till nearly today, not quite to today. And as many of you, I'm sure, know already, it's a sinusoidal wave. That during the winter, the numbers are generally going up, but in the spring, it starts in the northern hemisphere, it starts to come back down. In summer and spring, it's coming down, and then as the biomass falls back asleep in the fall, then the pulling out from the land decreases again, and the numbers go back up. In recent years, CO2 part per million in the atmosphere overall has been increasing at about 2 to 2.5 parts per million per year, a little less than the 2.5. I put this up just to show you that, yeah, we've been seeing this thing, that just like we saw exponential growth for years on CO2 emissions, we were seeing a curve up as well. Now I put this up to show this was that emission curve I showed you before. But now this is the total uptake from the atmosphere according to the global carbon reports. Each year, during the same time period, in other words, the total uptake. And you can see that this is typically equal a little bit more than half of the emissions in each year. CO2 uptake, whether it's for land biomass or for the ocean, is directly proportional to the partial pressure of CO2 in the atmosphere. As the parts per million go up, the intake from the sinks go up as well. And by the way, this is all normalized back to about 250 years ago when the parts per million were about 280. So this is not the entire flux, this is just the additional flux, because since 250 years ago, we've been increasing the CO2 in the atmosphere. If you trace this back, this curve fit line back, it ends up intersecting at about 280 parts per million, from years ago. And now this is another chart I produced. I produced this one and this one. So now I've broken up the sinks. Now, in this one, I also had the cement sinks, the concrete sinks that we create. This is just the land biomass sink and the ocean sink, and then cumulatives together. Steve, you remember this chart too? When I initially did it, because it's directly proportional to partial pressure in the atmosphere, I assumed a linear curve. For the ocean, it was very good fit. For the land, not quite so good. When I changed it to a quadratic to see what would happen, the fit got a little bit better. And you can see that, you can really see that here, that it makes sense that there's some curve here, more so for the biomass than for the ocean. But I'm going to tell you that I'm not convinced that that really should be assigned to the biomass. Because the truth is, when Friedland-Sting and his team come up with these numbers, they feel like they do a lot of really good modeling to help get the ocean number down, and the rest of it has to go to the land. So if there's error in their ocean one, it'll show up as variation in the land biomass one too. As they get better at that, we will simply know better. But I'm putting all this up to say that over time, what we're really seeing is that the combination of land biomass and oceans have continued to pull CO2 out of the atmosphere at a rate that makes it about 54% of what was put into the atmosphere each year. We shouldn't say that's the equation. It's really based on the partial pressure difference between what's in the ocean or the land and what's in the atmosphere. But it's about 54%, and it's been that way for a long time. So what we know from this is that the biosink and the ocean sink have both remained very strong. There was a period of time 25 years ago when the scientists thought these might be degrading. Then they recovered. They think they understand why now, but they are still very strong items. And we're looking at really